minimal surfaces. And people are thinking maybe, because think about it. What does this theory is telling you? What you call the theory of everything, the string theory. Okay, the multiverse theory. Then maybe we are in a membrane actually. So it's like a jelly-like thing in the water, or our universes are like the bubbles. They are just floating around actually, just going here and there in that liquid thing. It's not really liquid, but okay. So we have a membrane, and the universes are floating around in that membrane actually. Okay. So this brings in the possibility of applying what you call this theory of minimal surfaces. Okay, not minimal surfaces, but manifolds actually. Okay, into this understanding this what you call complicated kind of the universe, cosmos. So the word is not universe. Universe is a very local thing now. Okay, so technically universe doesn't mean everything. Universe means the place we are living in. So maybe we are living in one bubble out of zillions of other bubbles actually. Okay? So when you combine all these, you're going to call it a cosmos actually. So it's a cosmos. Cosmos or cosmos. Anyway. So that's a geometry basically currently we are using. It's a successful geometry, but people still find trouble with it. Then you have this guy called the Edward Witten, one of the giants of modern physics. He's so strong in mathematics that he has both. So he has all big physics prizes. I think he doesn't have a Nobel Prize, I think, but certainly he has a Field Prize in mathematics. He has a Nobel Prize in mathematics. Okay, and the kind of things that he's working now, if this becomes sensible, it's far away from experimentation. Maybe there will be some Nobel Prize announced in the future for him, because what he wants to do, so he wants to completely change the description of geometry, the geometry that we are. So he's saying maybe there is something wrong with our geometry, and therefore we are not able to come up with this unified theory of everything actually. Okay, so we don't have a quantum theory of gravity at the moment. Okay, so we can't combine quantum mechanics and general relativity. Maybe we are doing something wrong with the geometry. Maybe we can have something completely different. Okay. So he's kind of using a lot of knot theory, something that we find it uninteresting actually. So lots and lots of combination. He's a very, very nice guy. I mean, there's a discussion. If you get time, you must listen to it by Edward Witten, Abdus Salam, and who was the peer of the Abdus Salam who got the Nobel Prize? There was another guy. So Edward Witten, Abdus Salam. So they are, huh? Steven Weinberg, yes, you're right. Steven Weinberg and Abdus Salam and Edward Witten. So Edward Witten is the youngest of all. You just see this fascinating. So it's a black and white discussion, but they're discussing some of the amazing things. Anyway, so the major tool to understand this is again curvature of the manifold. What does the Gaussian curvature is telling us? So this is, we have time, so not doing mathematical calculation, just trying to interpret things that I want to do. So I would like to talk about what you call more about the Gaussian curvature. Okay, I'll prove a theorem actually, theorem proved by the Gauss. I think theorem gamma, something like that. Okay, which simply says that the Gaussian curvature is an intrinsic property of the surface. Okay, what do you mean by that? the remarkable theorems of the geometry. So it simply means that in order to compute the Gaussian curvature, you don't need any reference to the ambient space actually. At the moment what we are thinking, we have all surfaces but the ambient space is R3. Okay? So the Gaussian curvature is something that even can be observed by a bug who is a two-dimensional object, for example, and moving on a two-dimensional surface. You don't need a third dimension, okay, you don't need to visualize the third dimension in order to know the shape of, what do you call it, whatever the manifold that you have, the space that you have. Okay, so it's unlike the curves actually. I mean, if you remember, we proved the theorem in curve theory that if you take two curves, good has a definition, and parameterize by them arc length, locally they are same actually, they are not distinguishable. But in surfaces this is not the case actually. A plane and a sphere are two fundamentally different things actually. And that fundamental difference is their Gaussian curvature. Is the Gaussian curvature. Okay? So the sphere, we'll prove it, we'll see it, we can do computations that sphere has a positive Gaussian curvature, while the plane has a negative Gaussian curvature. The saddle, the plane has a zero Gaussian curvature. The saddle has a negative Gaussian curvature. Torus has different parts which has different Gaussian curvatures actually. Okay, so it's the Gaussian curvature that is distinguishing one, surface from other, and this is the intrinsic property of the surface. Okay. There are two principal directions. So one way is this. So either you move on these small circles or the bigger circles actually. So these will be the principal directions. Anyway, so K is K1, K2. Now, if at a point P, so if you give me a point on a surface, okay, so it's like I have a surface and give me a point here, there can be many curves passing through it with the different curvatures. Okay, but I can find the two directions, the two curves, which is going to have the the maximum and the minimum curvature. Are you getting the point? And their product is going to give you the Gaussian curvature. So at every point I can compute this K1 and K2. Now imagine different scenarios. If what? If K1 is different from K2, okay, and both are positive, what you can say about here? What do you mean by that?
Yes, better than 0.
Let me write the way he is presenting it. Here's the thing. If K1 is K2 is positive and the eigenvalues are also positive, so if K1 is different from K2, okay, and the eigenvalues are positive, in other words K1 and K2 are positive, then the point P on which you have computed this K1 and K2, it would be kind of an elliptic pointer. We call it, it's an elliptic point. So in other words, there are two curvatures, but they have different values. Okay. What would be the example of it? The example of it could be torus. Can torus have different curvatures at different points? So, how about cylinder actually? So it has a zero curvature in one direction and positive in another direction. So they are different. So any point would be, no,
It's
but it's not positive actually. I'm sorry? Rugby ball would be one of the, could be one of, so it's like elliptic paraboloid actually. So it's an ellipsoid actually. Let's call it an ellipsoid. So yes, this can have, different positive curvatures at different point actually. So if at a point on a surface, okay, has different positive curvatures, okay, different positive curvatures, you're going to call that an elliptic point. And by elliptic point, I mean that the neighborhood of that point would look like, is going to have an elliptic nature actually. It's not talking about the total space, the shape of the space, but at least that part is going to be. What would be the other case? How about if the product is negative? So in other words, then one of the point must be negative. Then, so in other words, the Gaussian curvature is negative. That's what I'm saying. Okay, so the Gaussian curvature is negative. So if the Gaussian curvature is negative, the point would look like how? So it must be something hyperbolic shape actually. I mean, if you, for example, see the springle, okay, so it looks like an hyperbolic shape actually. So P is gonna be hyperbolic. Okay, that's how the hyperbola looks like. But if I make a similar surface like that, like you have, as I said, this saddle actually. So it's in other words, that the neighborhood of that point is basically hyperbolic in its nature. What would be the third point? That what if the product is zero actually? Okay, the product is zero. So in other words, one of them must be zero. So P is, then P you're gonna call it is gonna be parabolic. Parabolic. Okay. I get your point. And as I yesterday also talked about it, that plane and slender, okay, and even a cone actually that you can make out of it, okay, you make a cone. They all have Gaussian curvature zero because one direction there is no curvature, in another direction you're going to have a positive. So from a differential geometry point of view, these three, surfaces will be indistinguishable. And that means that there must be some way to turn one into the other actually, without, cutting it or without, something like that. But you can't take a plane and wrap it around a ball completely. Smoothly कर सकते हैं wrap. So there will be some part actually, जहाँ पर you have to kind of, you're going to have wrinkles actually. It's not going to be smooth. So what does this mean is somehow the plane is different from the sphere, and geometrically what makes them different? That plane has zero curvature, Gaussian curvature, and sphere has a positive Gaussian curvature, and that's what makes them different. And similarly, sphere and hyperbolic, the saddle are different because they have different Gaussian curvature. So the Gaussian curvature is one of the key tools that tells you that what kind of surface you are talking about. Okay, that's one of the things. And mean curvature is important, but we're not mostly interested at the moment in it unless you want to do minimal surfaces. That is another completely different story.
The Gaussian zero, the P parabolic के हिसाब से the point
Gaussian अगर zero है, okay, so if the product of two things is zero, then you have two options. Either one of them is zero or both is zero. If if the both curvatures are 0, then it's something parabolic. Okay, something parabolic or plane. Parabolic and plane are, what do you call? They are almost of the similar meaning. There is no difference between this and this. Okay. Anyway, so if you take a cylinder and you look at the neighborhood of it, every neighborhood of it is going to look like a parabolic, roughly, patch. It's going to look like parabolic. So therefore you call it a parabolic kind of a point. Correct. Okay. For example, I can compute these both curvature. So here's the thing. So, and that's what I said here. So take a point, you can have different directions in which you can compute different curvatures. So here's the thing. Okay, let's take this paraboloid actually. So this has a positive curvature. So the principal directions are what? So this direction and this direction. So that's a minimal curvature, and that's the direction of the maximum curvature. But what if from this point I go in this direction? So this is also going to have a curvature. Okay, but this curvature in quantity is going to lie between this and this. It's a maximum and minimal curvatures actually. So there can be other directions in which you can find curvature. So it depends on that what kind of point you are. For example, if you are in a in a kind of a space, something like that. Okay, I'm doing very bad thing with the notes, but let's assume it like that. Now this is a complicated shape which is changing, its behavior from point to point. So if you take a point, for example, from here, it's parabolic. Okay, it has a 0 curvature. You take it from here, so it has some positive curvature actually. It depends on it that what kind of direction you are interested in to go actually. Are you getting the point? So curvature. So all this all theory is a local theory of surfaces. It's not a global theory of surface. Okay. So global differential geometry is okay. This is another subject. So what you are doing is local. You take a point and see that how does the space looks like in that locality.
For example, this cylinder है, उसपे हर point parabolic point होगा. ऐसा तो नहीं होगा ना कि कोई
हर point parabolic होगा. Yes.
और कोई ऐसी surface हो जहाँ पे एक point elliptic हो.
है ना, आपके पास, as I said, the torus example. So the top is parabolic, the outer side is, what do you call, elliptic, and the inner side is hyperbolic positive curve. Okay.
Hyperbolic inner side.
Inner side is going to be the hyperbolic, and other is going to be the elliptic. So it's a nice set of theories. It's a nice kind of description. These equations have meaning. Try to fetch maximum out of it. I was thinking,